Today we're going to talk about atomic structure and relative atomic mass. So Dalton's original atomic theory leads through a number of experiments to what we call the nuclear model of the atom. Now, if you have not read up on the history of atomic theory, I would advise you read up at least on the key experiments that led to the discovery of the nuclear model of the atom. So one of the big things that comes out of the nuclear model is that the atom has substructure. The atom is composed of a very dense, positively charged nucleus at the center, and then the electrons that Thomson discovered were in some type of loosely defined arrangement around the nucleus. So this is divided into two groups, the nucleus and then the electrons that surround the nucleus. We are going to look at hydrogen as our basic model. And in this, there are three main components. Orange guy first. The orange guy is going to be our proton. Now, protons have a mass, and it's, as you can tell from 10 to the minus 24, a really, really tiny mass. Okay? It's not important that you understand or know what the exact mass of a proton is. I want you to think of it in terms of relative sizes with the other objects that are coming up. Now on the charge, on the other hand, I do want you to pay a little bit of attention to that number, that 1.6022 times 10 to the minus 19th, and that's a coulomb, is that unit. It's a measure of electrical charge. All right. So let's go back here. Now the blue guy is a neutron. Note, neutron, roughly the same mass as a proton. It's a little bit heavier, but same order of magnitude. The big reason why we call it a neutron means neutral because it has no charge. Unlike the proton, which has the positive charge, and the electron, which has the negative charge, the neutron was actually the most difficult of the subatomic particles to find because it didn't have a charge to be influenced by machinery. Now, we've talked about the nucleus, the protons and the neutrons. What are their purposes? The proton is the identity of an atom. It is what the atom is. How many protons there are in the nucleus defines what element you're talking about. Right? However, you're starting to put more and more and more of these positive charges around next to each other in the nucleus as you get to heavier and heavier elements. And that's a problem because, as anybody who's ever played with magnets know, opposites attract, likes repel, right? So if I put two positive charges next to each other, they're not going to be attracted to each other. They're actually going to push each other apart. Well, that's the role of the neutron. The neutron conveys what's called the strong nuclear force. And what the strong nuclear force's job is to do is to hold all of those positively charged particles close to each other in opposition to the force of repulsion you're getting from the electromagnetic force. The strong nuclear force is actually much stronger than the electromagnetic force on very, very tiny distances. Distances smaller than the inside of the nucleus of the atom. So while the strong nuclear force is incredibly powerful and can act like a glue to hold the nucleus together, only to a point, because once you get to a certain size, the nucleus is actually too large for that repulsive force to be expressed across the entirety of the nucleus at once. So the protons are the identity. The neutrons are the glue that holds them together. This guy out here is the electron. Now note the mass of the electron. Again, not the absolute number I'm worried about, but the magnitude. Notice how we went from 10 to the minus 24th in the proton and neutron to 10 to the minus 28th in the electron. The upside of that means the electron is orders of magnitude, about 10,000 times less massive than a proton and an electron. And that comes into play in atomic mass because that allows us to not account for the mass of the electrons. They are so small compared to protons and neutrons, it would take way too many of them to actually have an influence on the overall mass. So we can effectively ignore the mass of the electron. The charge, on the other hand, this is the important number, 1.6022 times 10 to the 19th coulombs. If you remember, that's the same number as we had in the proton, only in the proton it was a positive charge, in the electron it is a negative charge. This is called an elementary unit or an elementary charge, right? Elementary charge is the kind of smallest whole charge you can deal with, right? So there's one elementary charge of a negative polarity in the electron and one elementary charge in a positive polarity in the proton. They cancel each other out, meaning atoms are electrically neutral. Now, what's the job of the electron? Well, the proton is the identity, the neutron is the glue, and the electron is where chemistry occurs. Chemistry is the exchange and the manipulation of connections with electrons. So that means that the electrons are dictating the chemistry of a system. Okay, atomic mass and mass number. We need to get out of the way. Back to our little atom of hydrogen here. We say it has an atomic number of 1. Atomic number is the number of protons. It's the identity, right? So if you look at your periodic table, it's typically in the top center of the box, right? Hydrogen 1, helium's 2, so on and so forth, right? Lithium, beryllium, boron, carbon, in case you guys were wondering if I didn't remember them, all right? We need to know the atomic number if we're knowing the identity. That number cannot change. We also have another number called the mass number. So the mass number of this atom would be 2. It has 1 proton and 1 neutron. Each of them has a relative mass of 1, which means that you get a total mass number of 2. Right? Mass number for an individual atom won't change, but each element can have various mass numbers, which we'll come back to. The number of electrons in the system equals the number of protons as long as the system is electrically neutral. If there's an imbalance, too many electrons, too few electrons, then that will lead to an ionic state. So let's talk about isotopes. So this is hydrogen. This is what we call hydrogen 1. Elements are named from their element name and their mass number. Okay, so hydrogen 1 means hydrogen with a mass number of 1, which means 1 proton, because you got to have that, and 0 neutrons, right? This is also hydrogen, all right? This is what we call hydrogen 2. Right? Note, they're both hydrogen because the atomic number has not changed. But they are different, what we refer to as isotopes, right? These are isotopes. Same element, different mass number. Now again, like I said, the number of neutrons for the most part doesn't change in an atom. So a particular atom is going to be a particular isotope. However, if I grab a billion of a particular element out of the air, it will be a mixture of different isotopes. We measure the mass, not the mass number. Remember, the mass number is simply number of protons, number of neutrons added together. The mass is measured in some physical unit. The atomic mass is measured in what we call atomic mass units. They're referred to as AMUs. They're also referred to as Daltons. 1 AMU is exactly 1/12 the mass of one atom of carbon-12. By the way, exact definition. Note, 1/12 the mass of one atom of carbon-12. Carbon-12 is going to have 6 protons, because it's carbon, that's how many you have, and 6 neutrons, because it's 12 total. Subtract the 6 for protons, you're left with the number of neutrons. So 12 minus 6 gives you 6. So 6 protons, 6 neutrons. We already know that neutrons and protons do not have the exact same mass. It's close, but it's not exactly the same. So what we're doing here is we're normalizing the mass across both protons and neutrons, because we're taking 1/12 of something that has 12 parts, 6 and 6. Okay? But this definition becomes important when we talk about mole in a later video. So let's look at breakdown of the hydrogen isotopes. Hydrogen 1 has a mass of 1.008 AMUs. Notice, not exactly 1. Right? Hydrogen 2 has a mass of 2.014 AMUs. not exactly 2 of the original. We're going to talk about why that is in a second. And then hydrogen 3 has an overall mass of 3.016 AMUs. All right, those are the 3. The average mass of hydrogen is 1.008 AMUs. What? That doesn't look like average. It is, but it's called a weighted average. All right, a weighted average means I give more weight to some parts of the average than others. In this case, it's very much skewed towards hydrogen 1. 99.99% of all hydrogen is hydrogen 1. Hence, 99.99% of the overall mass of hydrogen is that. So since that's the overwhelming amount, 1.008 AMUs is the actual mass of hydrogen. Now, how do I know these masses to these multiple decimal points? Well, we use a device called a mass spectrometer. It bends ions in flight through its system, and you can detect how long it takes them to get through the system. That helps us determine what the mass of an individual isotope is. We isolate an amount of that isotope, we run it through the mass spectrometer. That mass spectrometer is normalized against carbon-12. So everything is some fraction of carbon-12. Now let's look at magnesium. In magnesium, we have 3 major isotopes. Those are their individual masses. That's their percent abundances in the wild. That's how much of the total each of them contributes. So how do I get that number? I take the 23.99 AMUs of magnesium 24 and I multiply it by 0.7870. That percentage changed to a decimal point. So 78.7% of the total mass comes from this. That's like if I gave you a grade and I said, okay, 78.70% of your overall grade comes from these. You would be able to figure out what contributions your exams had to your overall grade. You can do the same thing here. So I multiply each of those through, I get 18.88 plus 12.53 plus 12.90. Add those 3 together, I get 24.31 AMUs. That would be the average mass of magnesium, the relative atomic mass of magnesium, right, is what we call it. Another example, neon 20 times 19.99 AMUs, right? Get 18.07 AMUs. Second one, you get 0.0567 AMUs, and then 2.03 AMUs. Add those together. You go to 2 decimal places because that's the shortest number of decimal places. You get 20.16 AMUs.